Now we'll take a look at a few other different things. Graduated cylinder, a flask, and beaker are all filled with water. The rate the water flows from the tap when filling the three vessels is going to be the same for each one of them. So take a look at the sizes. The graduated cylinder is this one. I know that's more like a test tube, but let's pretend it's a graduated cylinder. The beaker is this shape here, and then the flask is, of course, this shape with a wide bottom. Okay, so what I'd like you to do now is determine what the water level would look like as it's rising up with water level versus time. Okay, water level versus time. What would that look like for the beaker, the graduated cylinder, and the flask? Okay, so please pause the video and draw your graphs accordingly. Okay, so I hope you pause the video to do this, do some thinking on your own, because if you don't, then of course you're losing out on half of the power of these video lessons. So for the graduated cylinder, I'm seeing that it is thin and tall. The beaker is a little wider and about the same height. And then the flask is much taller but wider at the base and then narrower at the top. So I think I'm actually going to start with a beaker, and I'm just going to say that the water is going to basically fill up, and it's just going to rise at a constant rate as the water fills there. So I think I'll just start with this one, and it'll look something like that. So now if we compare the surface area of the base, or the area of the base, with the area of the base of the graduated cylinder, we notice that the area of the base is smaller here. So that means, what's that going to mean when the water fills up? Chances are it'll be filling up much faster. Okay, so in volume versus time, it's going to be a faster rate of fill, therefore taking less time to fill to the same volume than the beaker. And now for the flask, we know that the flask has a wide bottom, and then it gradually gets narrower and narrower on the way up, finishing off with a straight section at the top. So how would that look as water goes in and filling up to the top? Okay, so as we see that the radius of the flask gets smaller and smaller, that would sort of indicate there would be a bit of an acceleration of the rate of filling, followed by then a constant rate. Okay, so as the flask gets narrower and narrower, the rate at which the water fills is going to go up faster, and then followed by that straight section, the constant rate in the neck of the flask. Okay, let's now take a look at the bottom here, part B, again with water level. Now we have the graphs of two vases being filled up in the same technique, water level versus time. And now what we want to do is draw what we think the vase would look like as we were to fill that up to result in these graphs. Okay, so pause the video now and take a good look at those graphs and see if you can figure out what the water level would look like, or what the vase would look like, sorry. Okay, so when I look at these, to me it looks as though this one is going to be fairly wide at the base, and it'll be rising constantly for the first little bit. Okay, so there's going to be constant fill, and then we see that curve, which would indicate that probably the the top is getting narrower. Okay, so it doesn't necessarily have to be a curve. I would say it just kind of narrows as you get higher up along on the vase. So it looks something like that, I'm sure. Okay, compare that to yours. And then for this one, again, a little trickier. Notice how I have it starting slower, and then goes quicker, and then slower again. What might that look like? Of course, I always like to start off by drawing the most difficult part for you. And then what it could look like, there's a few different ways it could look, but I think I'm going to draw this like this. It looks something like that. I am no artiste, but that's how I feel this graph would be represented, or would be representing the water level in that vase. Okay, so we have a student in front of us, calculator-based ranger, and that student wants to get some sort of a graph, a distance versus time graph. And so we've got the idea that this walker is going to be walking slowly away at constant rate for 8 seconds, walking 8 meters. The walker is then going to pause for 3 seconds and then begin walking toward the ranger at constant rate for the next 4 seconds, walking 4 meters. Okay, so let's take a look at this. So for the first 8 seconds, they walk 8 meters at a constant rate. And so we know this is distance in meters. This is time in seconds. And so it goes 8 meters in 8 seconds. And then it pauses, the person pauses for 3 seconds. Pause up to the 11-second mark. And obviously when they pause, they're not moving, so their distance from the ranger is not going anywhere. And then they're going to walk back 4 meters over the next 4 seconds. Okay, so constant rate, if this is where the ranger is at distance 0, then the person walks further away, thus increasing the distance from the ranger over 8 seconds. Then they stay still for 3 seconds, meaning that they're still going to be 8 meters away. And then when they move back towards the ranger, their distance is going to get smaller and smaller for the next 4 seconds. Okay, so calculate the average rate of change over the first 8 seconds. So the average rate of change is delta D over delta T, and the delta D is going to be the change is 8 meters and the time is 8 seconds, therefore 1 meter per second. And the instantaneous rate of change at time equals 2 seconds, or time equals 6 seconds. Well, if this is constant, a constant rate right here, and over the whole 8 seconds it's 1 meter per second, then at the 2-second mark and at the 6-second mark it's also going to be 1 meter per second. Okay, so even though we can't calculate it, we know it's going to be that because the rate is constant. So the instantaneous rate of change is going to be the same as above, which of course is 1 meter per second. since the movement is constant.